What if you could turn a pile of old laptops, gaming PCs, or office machines into your very own AI supercomputer, built, optimized, and running your favorite AI models across a distributed network?
Unlike Open Cluster AI Station, EXO only splits models by layers, which can create bottlenecks and slow down inference, especially on heterogeneous clusters. Layer-level splitting limits how effectively weaker nodes or GPUs can contribute, reducing overall throughput. On top of that, EXO is notoriously more difficult to install and configure on Linux, often requiring complex dependencies and workarounds, whereas Open Cluster AI Station is designed to be simple, flexible, and hardware-agnostic from the start.
How to install and set up Open Cluster AI Station Beta. Open the terminal. Go to the GitHub page, copy the link, and download the program. Use the terminal to enter the folder. Use the chmod command to set the install script as executable, then run the install script. You will be asked for option 1 or 2. Option 1 will install the Python dependencies, so you can run the cluster matrix front end. Option 2 will install the C++ backend for cluster_matrix and compile it for you. This is a good time to take 5 to 10 minutes to hit the bong while we wait for the backend to compile.
For the backend to run properly, you must have the Ethernet interface set up. Use the following commands to configure it.
Once the backend is compiled, you are good to run the server backend by running the following command.
I like to control my clusters over SSH. Just log into your remote node using SSH, download and install the program, and then start the servers.
On the PC where you installed the full program, run the cluster_matrix_test.py Python test scripts in the Python environment that was created when you selected option 1 in the install script on the main head node PC. The test scripts are located in cluster_matrix/cluster_matrix_test_scripts.
If your tests run successfully, you're ready to start running the transformer inference scripts. First, download a supported model. It must be Mamba 2 or GQA, and place it in the following directory: open_cluster_ai_station_beta/llm_models. Next, you must cache the model weights across the cluster. In this example, we are caching an 8B GQA model. This is done using the GQA_cluster_chat_v1.py script. The script is designed to make cluster configuration simple. You define your entire cluster setup directly from the command line by specifying node IPs, shard distribution, backend type, and CPU/GPU usage.
What this means in plain English: model directory. You're telling the cluster which GQA model to load, an 8B LLMA-based model in this case. Node IPs. Each IP represents a shard of the model. Repeating the same IP means that machine will run multiple shards, allowing better GPU utilization on powerful nodes. Backend selection, llama. This tells each shard to use the llama/GQA backend for inference. CPU/GPU selection, 1. A value of 1 means use GPU acceleration on that shard. A value of 0 would force CPU-only execution. Node percentages. These numbers control how much of the model each shard owns. Bigger percentages equals more weights assigned equals more memory usage on that node. Weight cache mode, save. This tells the cluster to store the model weights locally on each node after loading them once. Pre-cache only. The model is loaded and cached, but no inference is run yet. This dramatically reduces startup time when you later run inference.
When this command is run, the system no longer needs to build or download any model weights. During the earlier caching step, all model tensors were already split and stored locally on each machine inside /dev/shm/matrix_shards. Because of this, the cluster can immediately map the cache matrix shards into shared memory and begin inference without any startup delay. The wait cache mode load flag tells the program to reuse those cache tensors rather than recreating them. In this example, the transformer is being run across 3 physical computers using tensor-level sharding instead of layer-based splitting. Every node participates in every inference step, but each node only processes the portion of tensors it was assigned during the caching phase. This allows all machines to work in parallel, regardless of whether they are using CPUs, GPUs, or a mix of both. The head node is the main controller of the cluster and is intentionally chosen to be the machine with the highest CPU clock speed, which in this case is an Intel i7-8700 running up to 4.6 GHz. This system coordinates the inference process while also contributing significant compute power. On the head node, 2 GPUs, an RX 6400 and an RX 5500, each handle roughly 30% of the model tensors, while the CPU processes an additional 10%. This ensures the head node is fully utilized and never sitting idle. The second node is a laptop with a low-power Ryzen 3 CPU and integrated graphics. Even though this machine is much weaker, it still contributes meaningfully to inference. Its integrated GPU runs about 10% of the model tensors, while the CPU handles another 5% using BLAS. This setup allows weaker hardware to assist without slowing down the entire system.
The third machine is a CPU-only desktop with an Intel i5-6500. It runs 15% of the model entirely on its CPU. Even without a GPU, this node can still participate in the cluster and provide useful compute power. Because the model is split by tensors instead of layers, all of these machines work together on every token generated by the transformer. CPUs and GPUs are freely mixed, hardware from different vendors is supported, and no single node becomes a bottleneck. By caching the matrix shards ahead of time and distributing the workload intelligently, the system is able to fully utilize all available hardware across the network, regardless of performance differences. This is what allows Open Cluster AI Station to scale from powerful desktops down to low-end laptops while still running large transformer models efficiently.
Next, we'll be loading and caching an SSM-based Mamba model. From a setup and usage perspective, this process works almost exactly the same as the GQA examples shown above. The same cluster configuration rules apply, including node IPs, backend selection, CPU and GPU usage, and tensor distribution percentages. The main difference is that instead of running a traditional attention-based transformer, you are now caching and running a state space model, which uses the Mamba architecture. Mamba models are built around state space mechanisms rather than attention, which makes them more efficient in certain workloads, especially for long sequences. However, from the cluster's point of view, nothing fundamentally changes. The model is still split at the tensor level, the shards are still distributed across the cluster, and the weights are still cached into shared memory for fast startup. When you run the Mamba caching step, the system takes the SSM model, divides its tensors according to the percentages you provide, and stores those shards locally on each node in /dev/shm/matrix_shards. This allows the cluster to load the model instantly later without rebuilding weights or reloading data from disk. Even though the underlying architecture is different, the caching workflow remains the same. In short, this step is simply caching an SSM transformer instead of a GQA transformer. The cluster logic, shard distribution, and execution model remain identical, which means you can switch between GQA and Mamba models without changing how your cluster is configured.
Once the Mamba SSM model has been cached, running it is straightforward and follows the same execution flow as the GQA models. Instead of rebuilding or redistributing weights, the cluster simply loads the previously cached tensor shards from shared memory and begins inference immediately. This makes startup time extremely fast and allows the system to focus entirely on computation rather than model initialization. When the run command is executed, each node maps its assigned portion of the SSM tensors from /dev/shm/matrix_shards into memory. Because the model was already split during the caching phase, every node knows exactly which tensors it owns and how much work it is responsible for. The cluster then synchronizes and starts processing tokens together, with all nodes contributing in parallel. Even though Mamba uses a state space model instead of attention, the execution model across the cluster remains the same. Tensor-level sharding ensures that CPUs and GPUs across different machines all participate in every inference step. Faster nodes naturally process larger tensor portions, while slower systems handle smaller shards, preventing bottlenecks and keeping the cluster balanced. The head node continues to coordinate execution, handle scheduling, and manage data flow between shards. At the same time, it also performs its own share of computation, ensuring that no resources are wasted. GPUs, integrated graphics, and CPUs can all be mixed together, and the system dynamically uses whatever acceleration is available on each node. Because SSM models like Mamba are optimized for sequential processing, this distributed approach allows long sequences to be handled efficiently without overwhelming any single machine. Cached weights eliminate redundant work, shared memory reduces latency, and tensor-based splitting provides fine-grained control over resource usage. In practice, running an SSM model feels no different from running a GQA model from the user's perspective.
The AI revolution shouldn't require $10,000 GPUs. This system proves you can run massive models on whatever hardware you already have: gaming PCs, old laptops, office workstations, even integrated graphics. If you've ever tried running AI models on Linux without an NVIDIA GPU, you know the pain.
GitHub link to code in description.
Thank you for watching. You fucking retarded fucking asshole fucks.